Hello, today I want to give an introduction to the p-adic numbers, and I'm not sure whether you've seen it that way, but I want to start with the following. So we start with the following theorem, namely Hilbert's Nullstellensatz. And let K be an algebraically closed field. So for instance, the complex numbers. And the claim is, so this is a weak version of the Nullstellensatz, there are also stronger versions. The maximal ideals in the polynomial ring in n variables, so we take k of x1 up to xn, are of the following form, namely x1 minus a1 and so on up to xn minus an with ai in k. Okay, I'm not going to prove it, but that's the statement. So let's have a look at the statement a little closer. So this basically means that maximal ideals are in one-to-one correspondence with points in Kn. So basically we just do the following. So we map x1 minus a1 to xn minus an to the point a1 up to an. Okay, so this gives us a one-to-one correspondence with points. Now let's look a little closer. So we have not only points but also functions. So the functions are polynomials. So if we let's make an explicit example. So let's take k to be the complex numbers, and let's take a polynomial in two variables. So let's take let me think why, or let's say x2 squared minus x1. So that's a polynomial in two variables, and now we want to evaluate it at let's say a1 is equal to so let's call this f. That's a function. We want to evaluate it at the point 1, 0. So that's our point. So we get f of a1, a2 is equal to, or maybe let's take 2 to make it not 2 and 1. Okay, so that's 2 squared. No, sorry. Okay, maybe it's 1 squared minus 2. So that tells us that that's -1. Okay, now let's consider the following maximal ideal. Let's consider the ideal, let's call it M. The ideal x minus x1 minus a1, x2 minus a2. So the ideal generated by this, and that's x1 minus 2 x2 minus 1. And now let's look at f mod our maximal ideal. Now what's that? So we can write it as, let's say f is equal to x2 minus 1 plus 1 squared minus x1 minus 2 plus 2. So that's x2 minus 1 squared plus 2 x2 minus 1 plus 1, I guess. And then we have minus x1 minus 2 minus 2. And now this is an m, this is an m, and this is an m. So this tells us that this is 1 minus 2, which is negative 1 mod m. So what we see here is that evaluation, and this holds more generally, so evaluation of f in k of x1 up to xn corresponds to reducing f modulo x1 minus a1 up to xn minus an. Okay, so now we have points and we have functions. So to make this, just to say it more clearly, so we can see the maximal ideals. So these are points, so these correspond to these points, and the functions are elements in the ring. So more general, so let me write it down. So the points are maximal ideals in this polynomial ring, and the functions are elements of the polynomial ring, so of this. So that's also a very useful observation in general for algebraic geometry and schemes and stuff like that, but we don't need schemes here. But we now let's generalize this. So let's go to the integers, and let's try to do the same. So the maximal ideals of the integers are of the form p for, so the ideal generated by p for p prime. Okay, so now let's look at so these are basically now our points. So we want to do an analogy. So what we want is an analogy here. So all that I'm saying is very sketchy and just a motivation. So we'll do a lot by analogy. And now, so this means that the points are primes. And what are the functions? Well, functions are integers. So functions are elements of the field, of the ring. So as before, this is also by analogy. So functions are element of the ring here, and the points are maximal ideals of the ring. So now let's see, how do we evaluate these functions? Let's take the function 12, for instance, and the point 5, well, we just reduce mod p, so let's maybe write it in like this. So f of 5, or maybe more like this. So we reduce mod f of 12, sorry. We want to evaluate the function. F of 5 is 2. And for instance, f of 7 would be 5, I guess, yeah. And so on. So we can evaluate these functions. So yeah. Okay, and now let's look closer. So can we maybe do some Taylor approximation of the function? So we want to approximate at the prime. So let's do maybe Taylor approximation for f equal to 12. So this is just 5, or the other way around, 2 times 5 to the 1 plus 2 times 5 to the 0. So that gives us 12, and that's just the usual base p, in this case base 5 expansion. And of course, if we would do like 25, or let's say 26, we would have 5 to the 2 plus 0 times 5 to the 1 plus 1 times 5 to the 0. Okay, so now we have Taylor expansion. And similarly, we could do Taylor expansions before in this polynomial ring. But for instance, if we take k equal to c, so here, if we take k equal to c, we get only polynomials. But over the complex numbers, we are not just interested in polynomials, but more generally in power series, or holomorphic functions. So holomorphic functions are locally power series. So we want to have power series. So now we want to have basically power series in the integers. So that would basically mean, again, this is, I argue, by analogy. So just informally, without worrying about convergence or anything, we want to have a sum, let's say from 0 to infinity, and then ai p to the I with ai in 0 up to p minus 1. So that's our power series. And now let's look closer. So over the complex number, if we use a usual power series, let's make an example. So let's look at, maybe I should, maybe I call it G for now. So G in C of, let's take one variable, and if we set this, for instance, to, let's say, 2x cubed plus x to the 4, maybe I write it the other way around. So this is expansion around 0. Of course, that's only a polynomial and doesn't have infinitely many terms, but we don't worry about that for now. So that's the expansion around 0. And the closer we get to 0, the less x to the 4 contributes to the value of g. So what I'm saying is just if we take so basically that the limit of x to the 4 plus 2 x cubed over x cubed for x to 0 is 2, and limit if we divide by x to the 4, then wait, is this what I want to say? I guess, let me see. Then this is infinite. So basically, yeah, x to the 4. What I'm saying is x to the 4 gets smaller faster than the x to the 3 term. So we want to mimic this behavior for the primes p. So and so what we want is that in some sense that 1 is larger than p. Let me write it like this already. It's larger than p squared, and so on, larger than, let's say, p to the n. And I write some. So this absolute value p is just to denote we want some absolute value, and we want that p is larger than p squared with this absolute value. Okay, that's what we want. Now let's look at the following. So if we really want an absolute value, so we want absolute value. So this means that we want it to be multiplicative. So we want, let me write it as, so first note that 1p is equal to 1 times 1p, which is 1p times 1p. So that means that this has to be 0 or 1, but we say it's not equal to 0 because otherwise everything would be 0. So 1p is 1, and also so now I can write the equation above as 1 greater than absolute value of p greater than absolute value of p squared, but now I can take the squares and the powers out. So we get this, and in order to have, so we can get that the absolute value of p is equal to some, let's say, yeah, so let's say some gamma, which is between 0 and 1. And now we can have a look at the issue of convergence. So first of all, as similar as for the power series over the complex numbers, we want we want to see what's the highest contributing term. So if, let's make an explicit example. If we put, let's say, f to be, let's take base 5 again, and let's put f 2 times 5 plus 3 times 5 squared plus and something else, then we want the norm of f to be the largest contributing factor, and these things here get smaller. So and basically we want to see it in the same way as for holomorphic functions over the complex numbers. So we say that this is the absolute value of the largest contributing factor, which is this one, and this is what's this? Well, we have 2p times 5p, and this one is just 1 because well, we want it to be 1 if it's basically smaller than p minus. So if it doesn't divide p. Okay, now we have an absolute value. And so maybe I go back to the rational numbers and maybe don't deal with power series anymore, but introduce them now in a more formal way. So for, let's say, for an integer n, we define the p norm, so to be the, we have to take some gamma in 0, 1 as the so let's say gamma to the negative, and then we take the, let's see, maximum over the m in C. Actually, we can take a non-negative such that p to the m divides n. So that's gonna be our p norm, and we take gamma to be 1 over p. That's just for convenience. So if you know about it, that's because we want to have for rational numbers adelic norm 1, but if you don't know what that is, don't worry about it. So that's the p norm, an example I've basically made above. So this here, we have that for, let's say, or maybe let's make the above example more explicit. So if we take n to be 3 times 5 squared, what's that? That's 75 plus 10, which is 85, and the highest power of 5, so what we have is that 5 divides 85, but 5 squared does not divide 85, so we get so this number here is 5, and so we get 1 over 5 to the, sorry, I think I messed up. Yeah, because I put a negative sign here because I thought we take p here. Okay, so 1 over 5 to the 1. And that's the norm of 85. The 5 norm. Okay, good. So we have this. And now we can extend this norm to Q. And over Q, we just define the P norm of, let's say, R over S to be the P norm of R minus the P norm of S. And now we have a norm on the rational numbers. So what can we do? Well, we can look at Cauchy sequences. So now we take analogy with the real case. So can look at the space of a Cauchy sequence or Cauchy sequences in Q with respect to this P norm. Usually for the real numbers we do this with respect to the usual norm we know. So let's look at the following. So, or maybe how do we do completion? So completion is the following. We basically take Cauchy sequences and identify null sequences. So sequences that converge to 0. And algebraically, completion is algebraically just the following. We take the, let me just write it out, ring of Cauchy sequences, so we can check easily that this is a ring. So the all 1 sequences inside, and this gives us a 1, and addition, multiplication is just pointwise. And now we divide out the ideal of null sequences. So these are the one that converge to 0. This is easily checked to be an ideal. So if we multiply by any, so Cauchy sequences are bounded. So if we multiply with a Cauchy sequence, it's still gonna converge to 0. And also if we add them and so on, we're gonna get another null sequence. And the null sequences are a maximal ideal. So we see immediately, using this observation, that the resulting algebraic structure is going to be a field. So how to see that they are a maximal ideal is also not hard. If we could add another element to this ideal, and we would still get ideal which is not the whole ring, then it would be not maximal. But if we add another element to the null sequence, then this is also going to be bounded away from 0. And then using this we can, so eventually bounded away from 0. So we can use this to get an invertible element by adding with a null sequence. And then we are done. So now let's look, let's define QP. So these are Cauchy sequences with respect to, with respect to the P norm modulo null sequences with respect to the P norm. So now we see immediately that we get a field. And this field is, so this is basically, we get Laurent series in P. So this means of the form n greater than or equal to n naught, an p to the n, and an is in 0 up to p minus 1, and we have subrings, so Cp, which are the power series, and that's what we've considered before. And so these are the p-adic integers, and actually Qp is just the field of fractions of the p-adic integers. Okay, so now we have seen some motivation why we want to consider these. We've actually constructed the p-adic. So let me maybe make a short recall. So we started with some algebraic geometry. We saw that maximal ideas correspond to points. We saw how we can evaluate function by reduction modulo and ideal. Then we did the same over the integers. We did Taylor expansion. We said that we wanted to consider power series and not just polynomials. Then we had reason, again, everything basically by analogy, to want to have this inequality. So basically, when we get nearer to a point, the contribution of higher powers should get smaller. And we use this to define the p-adic norm, and then we went back to the integers, defined the p-adic norm there, extended it to Q. We used it to, of course, one has to check that it's really a norm, but it is. And then we looked at completion algebraically, and we constructed the p-adic integers. And let me maybe finish off with a last remark. There's a theorem by Ostrowski which says that all norms, of course one has to define a norm, or no, yeah, norm, or should I call it absolute value? Well, norm or absolute values on Q are equivalent to P for some P, or the usual absolute value, which is often denoted by infinity, or sometimes -1 or something like that. And of course one has to define equivalence, norm equivalence, which is not hard, but which I don't want to do now. But basically this tells us that we have found all the norms already. Okay, I think that's it for today. Thanks for watching. Have a good day. Bye.